Every physical object in the universe is governed by two unseen rules: the identity of its building blocks and the specific ways those blocks connect to one another. By applying those two parameters, we can categorize all physical matter into four precise taxonomic groups: elements, compounds, mixtures, and molecules. Decoding matter begins with identifying its base ingredients. Every single physical ingredient available to nature is cataloged in one master index. This diagram is the periodic table, an index representing the roughly 100 possible atomic identities. To understand how the taxonomy works, we will highlight two specific squares: magnesium on the left and sulfur on the right. Every element is assigned a universal shorthand. Magnesium is a capital M followed by a lowercase g, while sulfur is simply a capital S. The infinite physical complexity of the universe is built entirely by combining these base ingredients in different configurations. We start with the most basic category of matter, the element. This animation shows the atomic structure of a pure element. In this sample of magnesium, absolutely every constituent atom is identical to the others. You can divide this sample infinitely, but the base atomic unit remains functionally identical. Now we shift our focus to the second building block from our index, sulfur. Transitioning to sulfur, the structural rule remains exactly the same. We have a pure field of repeating atomic units. However, these yellow atoms possess different physical and chemical characteristics than the gray magnesium atoms. That distinction means sulfur represents a separate elemental identity. An element's identity is derived entirely from atomic uniformity. If every atom in a sample matches, the sample is an element. Having defined isolated elements, we must ask what happens when these distinct atoms cross paths and interact. This leads to the second category, the compound. A compound exists when two or more different elements become chemically combined. This animation shows the precise mechanism of a chemical bond. The magnesium and sulfur atoms are no longer isolated. They are snapping together to form a rigid, repeating geometric lattice. Notice the strict architecture of this lattice. For every one atom of magnesium, there is exactly one atom of sulfur. This locked 1-to-1 ratio defines the chemical concept of fixed proportions. This microscopic bond dictates macroscopic reality. When elements chemically combine, they generate entirely new physical properties. Magnesium on its own is a shiny metal. Pure sulfur is a yellow solid. But the compound they form, magnesium sulfide, manifests as white crystals. The chemical bond acts as a physical barrier. Once elements are locked into fixed proportions, they resist separation. To strip a compound back into its base elements, physical force is useless. You must initiate a deliberate chemical reaction. Breaking those internal bonds requires an input of chemical energy, making separation highly difficult. Compounds act distinctly from elements sharing the same physical space. The chemical bonds create a completely new physical material. We can contrast the rigid, locked architecture of a compound with a state of unstructured proximity. This is a mixture. In a mixture, different elements or compounds coexist in the same volume of space, but they are completely devoid of chemical bonds. This spatial visualization illustrates the resulting chaos. The unbound magnesium atoms, unbound sulfur atoms, and the intact magnesium sulfide lattices bounce freely off one another, never attaching. Because there are no chemical bonds holding these specific components together, the concept of fixed proportions vanishes. The ratio of ingredients in any given mixture is entirely variable. This lack of chemical bonding provides a mechanical advantage. It allows us to separate the components using simple physical techniques, completely bypassing the need for chemical reactions. Scientists use physical processes like filtration, distillation, crystallization, and chromatography to sort mixtures based on traits like boiling point or molecular size. In a mixture, the elements and compounds share physical space, but they strictly retain their original, independent identities. This brings us to a frequent conceptual trap in foundational chemistry, blurring the line between compounds and molecules. The term molecule is purely a structural descriptor. It simply refers to any atoms that are chemically combined together. This diagram maps out the relationship. Elements and compounds are distinct categories defined by the identity of their atoms, but the structural boundary of a molecule bridges both categories. When different elements chemically combine, they form a compound. Because they are bonded, they are also molecules. Methane, water, and ammonia fit in this intersection. However, identical atoms can also chemically bond together. Chlorine gas and oxygen gas are molecules because of their bonds, but they remained elements because every atom is identical. Combining identical atoms forms a molecule that is an element. Combining different atoms forms a molecule that is a compound. Therefore, the term molecule describes geometry, not atomic identity. All compounds are molecules, but not all molecules are compounds. Stepping back, we can view the complete architectural framework of matter. This grid organizes the entire taxonomy using our initial two parameters: whether the constituent atoms are uniform or different, and whether they are unbonded or chemically bonded. In the first quadrant, matter with uniform unbonded atoms forms pure elements. In the second quadrant, different atoms that are chemically bonded create locked compounds. In the third quadrant, matter that is different and unbonded creates chaotic physical mixtures. And in the final quadrant, uniform atoms that are chemically bonded create pure diatomic molecules. This matrix serves a practical purpose. It dictates exactly how scientists must interact with physical materials in the lab. An object's placement on this grid determines whether you can rely on basic physical force to filter its components, or whether you must exert raw chemical energy to break it apart. Mastering this precise vocabulary of elements, compounds, and mixtures is the prerequisite for decoding the rules of the physical universe.